So welcome to Colin Butcher, who's going to talk to us this evening about systems infrastructure. We'll hopefully make about 50 minutes or so. We're not going to keep very strict time. The talk's going to last for however long it lasts, but I'm expecting it'll be around about that. And then we'll save some time at the end for questions. There is a chat window, so unlike GoToWebinar and other things, there's only one chat window. We don't have a separate questions window. We just have the chat window. Please do use that. Please do stay on mute during the talk though, but please do use the chat window for asking questions, and I will collate those questions and pick out the good ones at the end to have Colin address. So without any further ado, I will now hand over to Colin. I'll go on mute and I'll hide myself. And Colin, over to you.
Great, thank you very much. So I've been designing and building systems and data networks and all sorts of crazy stuff for the last umpteen years. And I find that a lot of people don't particularly know much about what really happens inside places like data centers and all that kind of stuff. So the idea of this talk is to kind of cover quite a lot of it, not in too much depth, just to point out all the bits and pieces that exist and some of the things that we have to worry about when we're designing or troubleshooting systems and infrastructure. So here's the agenda, which will pop up occasionally as I change sections. So a little bit about myself. I've been doing this kind of thing now for probably 35 plus years. I used to help run a software company as lead designer, and we did lots of things like ground control centers for flying spacecraft. So pretty much everything I've got involved in has been mission critical. All this computing stuff is my second career. I'm originally a mechanical engineer and then jumped sideways into control systems and kind of went from there. And for the last 25 years or so, I've run my own company as a freelance consulting engineer, designing and building mission critical systems, predominantly based around VMS operating system and all the associated hardware that goes around that. And I'm now at the point in my career where I think it's really important to pass on knowledge and information to help other people. So one of the big problems for me with all this computer stuff is that it's become pervasive, and I don't think enough people understand it very well. And so a lot of projects fail, and a lot of systems occasionally go wrong, and it's difficult to find people who know exactly what happened and how to fix it. And that's bad news, particularly if it's very mission critical, which is the world I've been working in for a long time. One of the things I believe is that what happens is that most of what we deliver doesn't have any physical reality. You can't touch it, you can't feel it, you can't see it. And things are getting more and more complicated, so that problem's getting worse. So what that means is that we need really good conceptual skills to be able to explain things to other people and to communicate ideas clearly to each other. There's a really great book, The Mythical Man Month, by a guy called Brooks, who led IBM's building of the OS 360. And he writes really nicely about this problem of communication and how teams of people work. So if none of you have read the Mythical Man Month book, I thoroughly commend it to you. And again, it's mostly a people thing, which is bizarre for a technology industry. It's all this mismatch of expectations and not quite understanding what's going on and expecting things to happen really quickly and be got, one of the unreasonable things, many unreasonable things, is businesses expecting people who haven't done something before to get it right first time, and have a pretty tight timescale, and in many cases, the budgets aren't quite adequate. So you'll often have timescales and budgets are set before understanding what it is that you're really trying to do. So it'd be nice to see the industry do a better job. So I'm kind of hoping to help that a little. I still think it's not really an engineering discipline yet. It's still very much an art and a craft. It's a bit like the early days of mechanical engineering. If you wanted something really well, you went to the people who did it really well. And the knowledge about doing that wasn't as widely available as maybe you'd like. Things are often poorly documented and not terribly well explained, so it makes it hard to control what's going on. IT industry is terrible because everything is changing so fast all the time. However, I do believe that if you've got a really good grip of the underlying principles, those don't change too much, and therefore it gets a little easier. And it's all about people and communication and getting clarity on what it is that you're trying to do and how things work. So moving forwards, let's look at some of the key things when we're designing and building systems and infrastructure. So availability, performance, and security are the kind of the three biggies for me. Lots of people worry about performance. What I think they're actually worrying about is availability, but they express it in terms of a fear of something failing to perform, because their experience of systems that fail is they fail because they don't meet their performance targets. Similarly, security. If a system's not very secure and it gets taken down, it's no longer available. So the real problem is availability, but it often shows up as people thinking about performance and thinking about security. Performance-related failures are awful to debug. They're very often transient. You very often don't have continual logging and collection of information. So figuring out what happened afterwards can be really difficult. And of course, that nice Mr. Heisenberg gets in the way as well, because the moment you turn all the logging on, you change the behavior. And so it's kind of difficult to figure out what's really going on. Similarly, security attacks can affect performance. And as a designer, what you're generally trying to do is to make sure that the systems and the infrastructure have got sufficient capacity and performance to deal with the workloads in an acceptable period of time. And the real thing here is under recovery conditions. So having a system cope well under recovery conditions is usually the point of peak workload, because it's also having to shuffle data around, check the data integrity, and do all sorts of other good things. So important challenges within systems and infrastructure design: we have to protect the data. We really don't want to lose anything, and we really, really don't want to corrupt anything. Losing the systems themselves can often be bad enough, but losing the data, game over. And that's been behind some of the high-profile outages over the last few years, is having to put the data back together. And you can be down for a long time. I think British Airways was one of the ones a while back. They were out for nearly 2 days. And some of the banking systems have had some fairly high-profile failures. But as a designer of infrastructure, there are things you can do to reduce the probability of failure by making sure there are no single points of failure, and that everything's running out of multiple data centers. And there are also things you can do to minimize the extent of a failure, sort of contain it, if you will, by segmenting the systems and infrastructure so that failures don't just propagate through willy-nilly and take the whole thing down. One of the other things that I've come to believe is quite important is lots of people have kind of walked into running a 24/7 service, but their infrastructure wasn't really designed for it. So I rather flippantly refer to it as running a 24/7 service with a 12/5 infrastructure. But if you think about it, a business that's maybe been running 10, 12 hours a day, 5 days a week, and then they've suddenly discovered internet sales, and they've discovered all sorts of other things, and the pandemic has struck, and there are people working from home as and when they choose, and there's more flexible working, all sorts of things like that. They've ended up being in the 24/7 business when they didn't really mean to get there. And they haven't really designed the infrastructure and everything behind it to handle that, but that's where they are. And now they're kind of running along, sort of with their fingers a bit crossed, sort of going, well, we really hope that doesn't quite go wrong today. But if you've designed it as 24/7, then you can cater for things like hardware replacement. You can cater for things like change over time. Cater for things like keeping your software and firmware up to date. And these are important from a maintainability and supportability point of view. And how can you do maintenance while it's working? Well, if you've designed it carefully up front, actually these things are possible. You can even do things like move an entire data center somewhere else without ceasing to deliver the service you're trying to deliver. It's not easy, but it's doable. You can also cope with changing workloads. And some of the big things that are important here are monitoring, remote control. Especially now with the pandemic, you may not have physical access to the data centers. So the ability to monitor and remotely control things is ever more important. as is continual training and information and documentation. Keeping people informed and ready to respond when something bad happens is really important. And there's a weird paradox here in a 24/7 world with ultra high availability, disaster tolerant systems, which is the systems themselves will do their level best to keep running regardless. And it's only when the second or third failure happens that the thing goes down. And so the monitoring and remote control and remote diagnosis and the ability to get stuff fixed is actually even more important, because the systems are doing their best to hang in there, even though bits of them have fallen off. That's a really interesting paradox. And that's where being hyper aware of what's going on is important, because you need people to be aware that something has happened and then go do something about it before the second or third failure strikes and takes you down. Something else that's worth pointing out is that within data centers, we've got all this, sophisticated equipment. So we've got servers, we've got storage arrays, we've got data network switches, we've got routers, firewalls, storage arrays, storage switches, all sorts of stuff, and huge plethora of end user devices out there. They're all just working the same way, fundamentally. They're all specialized types of computer which work in a vaguely similar manner, but the key thing is they're governed by similar principles. So how they work in terms of performance, how they work in terms of parallelism, latency, and these other things are actually all largely the same. So once you've got a good grip of the underlying principles, you can start applying those to all these disparate bits of equipment, and it makes it a lot easier to get your head around how the whole infrastructure hangs together. This is what I call the Hall of Mirrors effect. You've got lots and lots and lots of things going on out there. You can't see it all. And often your view of what's going on is distorted because of things like layers of virtualization. And hiding things behind abstraction layers, things like that, makes it easy to deal with the bits you're interested in, but it makes it much harder to get a grip of the whole thing, especially if there's a problem that you're trying to diagnose and find out. So as a designer, it helps if you can figure out which bits of the system are mission critical, which bits don't matter too much, which bits might be safety critical. That's a different thing, because you want it to fail in a safe manner, not a dangerous manner. And you want good information about the different kinds of failures. And can you detect them? And a question I always like asking is, what kind of failure do you prefer? So you might prefer the system to fail in a certain way to another way. So two extreme examples of that. Let's say it's an air traffic control system and you're catching the radar returns. Do you want the system to bog down and try and hang in there and miss more and more radar returns, bearing in mind that the closing speed of aircraft is something ludicrous, and you're rapidly losing track of where everything is? Or do you want the failing system out of the way and something else stepping in and taking over real fast? I think you want the second under that circumstance. On the other hand, if it's the end of year batch reconciliation of some monster banking system, which is running for forever and it's bogged down, it's already got most of the way through it, it's got a few hours left to run, but it might impact service for the next day. You probably want that to finish rather than blow it away and have to start again another day. So it's a very different failure scenario. So you would set things up differently and think about how you might want the system to fail, and that helps guide you as a designer as to how you might configure things and how you might segment the infrastructure and the systems and be able to make changes while it's working. I quite like the quote at the bottom. It's not mine. I wish it was, but it's great. Everybody's got a test environment. Some are lucky enough to have a separate environment for production. I think it really captures the problem quite neatly. This is worth touching on briefly, because lots of people worry about performance. I think there are three underlying principles that govern performance. One of them is bandwidth, which determines throughput. So it's units of stuff per second. So if it was a motorway, what is it? Is it people per hour, vehicles per hour, or tons of goods moved per hour? So you just got to be a bit aware what it is that you're measuring, but bandwidth is the thing that determines throughput. Latency is the thing that determines response time. It's also the thing with storage that determines write rates. The subtlety here is that if the latency is considerable, there might be a lot of data in transit, and that's the data in transit or the data in flight that's going to evaporate if there's a failure. So you then have to do retransmits, things like that. So it does have an effect on bandwidth as well, in terms of how much data you're really having to shift because of retrans. And then thirdly, there's a thing called jitter, which is mathematically it's diff latency, it's variation latency with respect to time. And that's the thing that usually is behind weird and wonderful system failures under spikes in workload. Because the latency starts fluctuating too much, the systems can't handle the spikes in workload very well, the latencies change, they become much worse, and you trip over timeout values and things like that. So those three properties are worth understanding. And they also govern data networks behavior, they govern storage behavior, and the extent to which systems are, the current buzzword is oversubscribed. So if you oversubscribe a data network and everything happens at once, you're going to bang into problems with jitter, and similarly with storage. So as a designer, when you're looking at the performance and thus availability, you need to be aware of saturation and contention for resources. Those are the biggies, because you're trying generally to size your systems to cope with peaks in workload, similarly with the data network stuff and the storage network stuff, or the infrastructure pieces. And it's really about eliminating wait state. So the sort of jokey comments down the bottom kind of come in. You know, we're not trying to make it go faster, we're just trying to stop it going slower. And things like that are quite important. One of the other problems I find with a lot of people writing software is they're very good at thinking about sequential stuff. They're not very good at spotting the possibilities for parallelism and thinking parallel and doing more things at the same time. And the whole thing about infrastructure design is, particularly data networking, storage networking, often the more paths you can get running in parallel, the greater the performance you can get, because you can drive the latencies down, you can drive the bandwidths up. And so finding people who can see how things can best work in parallel rather than sequentially is really important. You know, it might be that you're doing backups. So you might want to be spinning off copies of data, you might want to be pouring data out to tape, you might need to then put resynchronize data, you might want to stop the database and start the database, all those things. And actually, you can pull all those apart and kick them off in parallel on different services, and you can then bring the outage point right down to a very short period of time. Lots of things to think about. We also have to design for security. So can we detect security failures? Because if we don't know that we've been compromised, then that's really unhelpful. We also have to understand the regulatory frameworks that we're operating within, you know, what logging we might need, how long we might have to keep the data for, or log data for, all that stuff. We've got to have good security policies, bearing in mind that the landscape we're working in keeps evolving. And there are people in places like Cheltenham who have a public side, and they're about providing information to help people keep their systems secure and look at things. And we have to worry about the data when it's in at rest and in transit. And again, segmentation, firewalls, things like that come in order to help limit the scope of an attack. So in the same way that we can limit the scope of a failure by segmenting the infrastructure and the systems, we can similarly segment how far a security attack might go, or we can equally segment how far a performance failure might go by thinking about how we lay the systems out. That's enough of the conceptual stuff, because that's quite a chunk of thinking in there. Let's very quickly look at some physical infrastructure in a data center. So equipment sits in racks. Typically it has dual power feeds. You know, you've got two sets of UPSs. Behind that, you've usually got two sets of generators. There's an awful lot of cabling, both copper and fiber. And airflow management is terrifically important. Usually it's front to back. So make sure you do things like mount your data networks, which is the right way round. I have seen it done where the airflow is going the wrong way, and then it's very easy to cook something and then things go wrong. So there's a lot of detail that you have to pay attention to here. Color coding I find really important as well, you know, even to the extent of putting, you know, colored labels on bits of equipment and on the cabinet so you know what's going on. It's particularly true with data network cables, things like that. There's an amusing story from years ago. One place I went, they had lots of multicolored cabling in a big tangle. Trying to work out what was going on. I expected the color coding to be, red might be inter-switch connectivity, blue might have been servers, yellow might have been telephones, and so on and so on and so on. So I asked the guy what was going on, and his color coding convention was length, which was not what I expected. Made loads of sense to him, but it wasn't as helpful as you'd like. Labeling is also really important. So labels should tell you what a cable is doing, where it goes at both ends. So it goes from, switch thing, port something to wherever else it goes to, but it's got to have the information on it, because you might be tracing it through a whole collection of patch panels in order to arrive at a piece of equipment that then sends the data off to another site. And knowing all of that is really important, especially in high availability mission critical systems where you've got multiple paths. You don't want things connected up wrong. Otherwise it will go wrong when you're not expecting it. And monitoring controls really important. So OOB stands for out of band management networks. That's how you know whether the power's good. It's how you know whether the equipment's running. It's how you reach things like the consoles or the ILOs for the switches, for the servers, and so on and so on and so on. And the problem gets more and more difficult if you're buying space in data centers. So if you've got a big multi-tenant data center, you've also got to start worrying about things like physical access control to the racks or region data halls within the data center, things like that. So there's a lot to think about. This is a very small installation. It's only a couple of racks at one data center. So for those of you familiar with the stuff, the yellow things are 3-part storage arrays. They happen to be very fast ones because they're all flash, and the servers above are all Itanium-based machines with large amounts of memory and high core counts. So this is a pretty zippy system, and doesn't look terribly much from the front, except for the bit at the top, which is the data network switches, and you can see all the carefully color-coded cables with lots of labels on poking in and out of the switches, which is great. And at the right-hand side, it's a back view of one of those two racks. And again, you've got vast amounts of color-coded stuff, and the sort of aqua and blue stuff to the left and up to the top is actually fiber optics rather than copper. And the big, thick red and blue lower down are left and right power feeds, and just above that, you've got black and gray power feeds, because it's really helpful if the power feeds are also color coded and you know that everything is properly dual powered off both sides of the back of the rack, which then go back to the correct power trains, and so on and so on and so on. And that's the kind of diagram that goes with it. So there are two racks, there's the equipment, and there's all sorts of bits of information on there about things like weight, because floor loading matters, and power consumption, because airflow and cooling matters, and power feeds in matter, and so on and so on and so on. There's lots and lots and lots of detail hiding behind getting stuff in and running. So that's a bit of light relief. Now, how do we connect to these systems from wherever we are? So data networking, the predominant technology these days is Ethernet. So Ethernet works by having frames which carry the data. And the front end of the frame has got the hardware address, the physical MAC address, we've got a broadcast address, multicast addresses, things like this. So within the Ethernet frame, we've got these things, and this has got nothing to do with the protocols we're running over it. So this is all about the Ethernet frames on the network, which could be carrying any of a range of protocols. TCP/IP-v4 is a protocol, TCP/IP-v6 is another protocol, DECnet would be another, SMB might be another. There's a whole string of different layer 2 protocols and layer 3 protocols, but they all sit within Ethernet frames, and then that makes up packets. And there's 2 Ethernet formats and so on. There's a thing called Wireshark. If you're interested in these things, Wireshark packet capture and the associated documentation goes into an incredible amount of detail that's really useful. Oh, you also get things called jumbo frames, where these days with gigabit Ethernet, we've got much greater bandwidth than when Ethernet was designed, which was back in the days of 10 megabits, using big, thick, yellow coax cable. Jumbo frames is about increasing the payload to the number of checksums because the transmission medium's got more reliable, and lots of people still don't turn jumbo frames on because they're a bit scared of it. You do need all the switches that make up the infrastructure to support jumbo frames, but they're worth turning on because you'll get a much greater throughput because the ratio of data to overhead in the frame size is much better, much more favorable. Segmenting networks is really important. You know, we can segment them for network, for availability, performance, security, just to separate out the different traffic flows. You might need multiple NICs in your systems, or you might be using VLAN tagging out of your switching, out of your systems into the switches. And segmenting a network infrastructure is really worth considering. And most big data centers have to do that, especially the multi-tenanted stuff. Everything is heavily segmented to make sure that, you know, clearly one customer's data can't see another. And you might be doing something similar on a small scale at home. You know, you might want to keep your kids' data away from your office at home data, for example, or you're, you know, watching TV and music stuff away from your Zoom conference at home stuff, and you might need to prioritize one kind of traffic over another through your router at home. So the same principles apply to working from home as they do to the big stuff. So the big thing that makes network work is Ethernet switches. Basically, they're about introducing parallelism as a principle. So two switch ports can be talking to each other like crazy while another set of switch ports are talking to each other like crazy, and the traffic isn't bumping into each other because it's only going in and out of the ports it needs to go in and out of. It's all down to speed of chipsets. Latency and bandwidth are really important. And if you've got single devices, you can switch from sort of half duplex operation to full duplex operation, actually have traffic going in both directions at the same time, which is one of the things behind gigabit Ethernet as well. You also, in the bigger switches, to try and figure out what's going on if things go wrong, you need sophisticated means of traffic monitoring. You might turn on mirror ports to look at packets, all sorts of good things like that. And if you've got lots of big switches and you need serious amounts of bandwidth, you're probably doing link aggregation. Or it might be that you've got a server with only 1 gigabit ports, but it's got 4 of them, and you don't really want to put a 10 gig port into a server, but you can aggregate up the 4 1 gigs, and there's a mechanism called LACP, or bonding on Linux, another thing, or lots of other operating systems give it different names. So you can aggregate up links and get more bandwidth that way. And then you control the bandwidth with things like quality of service, and so on and so on and so on. Key thing about Ethernet switching, though, is it's store and forward switching. So packets or frames come into the switch and then they're moved out. And that's largely around reading the headers and also coping with the differences in speeds in the early days. And then we have layer 2 to layer 3, layer 4. And layer 2, layer 3, layer 4 really refer to the TCP/IP protocol. So layer 2 tends to be protocol independent, MAC address based down at Ethernet frame level. Layer 3 is generally referring to the TCP/IP routing layer. Layer 4 is generally referring to the kinds of TCP/IP traffic it is, such as HTTP or HTTPS. It's worth just, yeah, these terms get bandied around a lot in general conversation with network people. It's just worth being aware of what they're actually referring to. VLANs, virtual LANs. LAN is local area network. These are another way of segmenting a network. So you can group up a bunch of ports and declare that that is a VLAN. A different group of ports might be a different VLAN. And the mechanism behind it is called VLAN tagging, 802.1q. And so you can do port-based VLANs. You can also do protocol-based VLANs. You can do connectivity between VLANs. You can prioritize one over another with quality of service, and so on and so on and so on. You can also get the servers to do VLAN tagging out of the back of the server. And so the server starts behaving a bit like a switch. And that way you can direct different traffic flows into different switches. Now that can be a useful technique because you might want to boot a server into different environments. And as we all know, what the server, how the server is configured is held inside the operating system. So if you boot from the right place, you get your VLAN connections correct. And that way you don't have to go and mess with the switch configurations when you boot a different boot image. because you've set the switch ports up as tagged ports, you've enabled the VLANs that you're going to expect to come in from there, and depending on how the server boots, then it connects up to the correct VLANs and the traffic flows. It's also worth looking briefly at wide area network technologies. It's quite a history lesson in here. So, some people might remember ISDN, POTS is plain old telephone system, and dial-up modems and things like that. But if you're working in other countries, you might trip over some of this stuff. So don't dismiss it as being out of date just yet. And also, systems that have been around a long time might still be working on some of these technologies. So it's worth being aware of it. It's also worth understanding where some of this stuff comes from, because it helps you understand why some of it's done the way it is now, because of the backwards compatibility aspect. These days, most of the stuff we're going to trip over is going to be VPNs or MPLS, things like that, and lots of encapsulation and tunneling. Routers are important. They take traffic out of our local network and move it to someplace else. So within TCP/IP v4, this is where you jump out of one subnet into another. You have to go through a routing function to do that. And quite a lot of switches are layer 3 switches, and they'll do routing within the switch, which is kind of a neat trick because that gets the latency down and gets the throughput up. But if we're going off to someplace else, we might have to go through dedicated routers, or in some cases, dedicated firewalls. And don't forget, the little thing you're using at home that connects you to the outside world is a combination of a router, a firewall, probably a modem, probably a switch, and a whole bunch of other cleverness. Oh, and a Wi-Fi access point as well. A whole bunch of cleverness all jammed in one little device. But the functions are different. So that's what routing does. And IPv6 is really common in the big stuff. That's how big backbone networks tend to work these days, because we're running out of address space. And encapsulation is a neat trick for handling other layer 2 protocols that are non-TCP/IP. So we pull the packets off the network, encapsulate them, route them through probably a TCP/IP mechanism, and then put them back together and back on the network at the other side. Firewalls are really important. And these allow us to inspect and block traffic flows. So as the threat landscape around us changes, people get firewall updates and things like this. There's an awful lot of stuff in the infrastructure that has to be set up correctly and might change relative to something else. Some new version of an attack turns up that you might need to introduce a new firewall rule. With any luck, it's isolated, but you just want to make sure and check things. And firewall performance can really affect traffic flows. So often firewalls have got very high performance silicon hiding inside them in order to not hamper the traffic flows too much. Systems tend to have multiple network interfaces these days. Go back a long time, everything came with, and Ethernet was a lot. These days, 4, 8 NICs is really quite common. And so aggregating them up gives us different ways, and different operating systems over the years and different switch vendors have done it differently. So Linux talks in terms of bonds, Windows will talk in terms of NIC teaming, VMS, an operating system I'm familiar with, will talk in terms of LAN failover. Cisco as a manufacturer will talk in terms of Ether channel. Other switch vendors will talk in terms of LACP, and so on and so on and so on. There's lots of different terminology floating around. They mean similar things, but they're not necessarily interoperable. LACP is kind of a standardization. So if things are doing LACP, they're supposed to work together, and mostly they do. So that gives you a bit of a clue from a diagram point of view what happens if you've got tagged VLANs coming out of somewhere. It hits an LACP virtual device. So you've got 3 virtual devices down the left-hand side representing your 3 VLANs, feeds into an LACP virtual device. That then feeds onto a couple of NICs. That then feeds onto a couple of switches, and the traffic flows. So that's dealing with multiple paths. Different switch vendors will do it differently. Cisco's Ethernet channel, HP Procurve, now Aruba does meshing. Extreme Networks does a neat trick called each ring. That works really well, by the way, if you're replacing FDDI stuff. So you can aggregate up the interswitch and the switch to server links to get us much more bandwidth. That's where the LACP thing comes in. Interesting twist to having multiple paths is that packets may not arrive in the order in which they were sent. That's why packets are sequence numbered. It's why retransmits can happen. It's why some protocols have an out of order packet cache, so they put the packet data back together without having to do the retransmits. Glitches in the links can cause traffic disruption, backoffs, all sorts of clever stuff like this can happen. And we can also end up with extended distances as well. Beware the VLANs extending across multiple switches. One of the tricks that some switch vendors do is auto propagation of VLANs to switches as you add them. That can save you a lot of time. It can create you a lot of trouble depending on how what kind of a day you're having. TCP/IP v4 is the predominant protocol that most of us see on the day-to-day basis. So layer 4 is the top layer, which is the HTTP and other sub-protocols based on the port numbers. Layer 3 is the IP addressing and routing layer. Layer 2 is down at the MAC address layer, and layer 1 is the physical stuff. Then we got all the sub-protocols of TCP/IP. Most people will be aware of things like DNS, DHCP, SSH and Telnet come up, NFS file serving, and so on and so on and so on. All these are different mechanisms and need to be understood and set up carefully so that you've got higher, so with DHCP, you'll probably want multiple DHCP servers, and you might need to give them different ranges so they're not handing out addresses in the same range and getting a conflict. Similarly with DNS servers, you'll want more than one DNS server. Oh, and you want time servers, things like this. So all of these things in here, if you're setting up big infrastructures, you need to think about, NTP as well for time synchronization. All of these things need considering as to how you're going to provide them in a high availability manner in a big infrastructure spanning multiple data centers. It's also worth, from a designer's point of view, thinking about service addresses. I often come across systems where the machine might have a single IP address. Actually, what it could really do with is a set of IP addresses, and then you can take an address down and bring it up on a different system, or you can point a load balancer at it, or all sorts of other things like that. And then you can offer the service from the service address, but keep the system addresses up. So for example, let's say you've got a system offering a database. You might want a management address that you can always reach the system by. You might want an address on the NIC that you can always probe to make sure that the servers are live. And you might want an application service address that is only up on that system when the database is up and running. And you can have multiple IP addresses on the same physical interface. And that's something that's really, really helpful. And I don't see enough people thinking about this and doing it. But that's well worth looking at. And packet flows are important. Think about how the traffic's going to flow. Think about where the retransmits might happen if something bad goes wrong. Think about all sorts of things. There's a bit there about how you might design network protocols. Ages ago, I did in fact get involved in designing a network protocol because we were trying to do very high availability data flows with very low latency. So we ended up, it was a long while ago, designing and building a specific protocol that did multicasting over multiple physical LANs. And statistically, it turned out that if one of the LANs went, the data would still get through most of the time. And so the protocol we designed ended up transmitting it down all of the LANs at the same time. And it was the receiver's job to throw away the duplicates. So understanding packet flows can give you some quite neat advantages. It was a much better method of doing it than doing IP multicast, things like that, because we were trying to really drive the latency down. That was the problem we were trying to solve. How do you cope with bad latencies and jitter? How do you cope when things aren't quite working? So all of this has to be thought into the packet flows inherent in choosing which protocols you're using and how you're going to configure them. Another good question is, where's your data? So this is about the storage side of infrastructure. So we've talked about some of the underlying principles. We've talked about what some of it looks like in a data center. We've talked about how we connect up. And the bulk of the talk, to be honest, has been the concepts and the data networking thing. From here on in, storage is probably less of it, and then some of the server stuff. So storage area networks, or SANs, they're the connectivity between the servers and the storage. They aren't the storage array. I hear too many people talking about a storage array being a SAN. Oh, we bought a SAN. No, you've not. You've bought a storage array. The SAN is the connectivity between them. The two predominant things are iSCSI and fiber channel. So iSCSI is providing connectivity, which is using data networking technology. So it's IP based. So it's internet SCSI. And fiber channel is specifically designed for storage networking. And SCSI commands are transported over the underlying connection. So fiber channel is a bit confusing. So fiber channel is also the name of the protocol. So it's designed for storage traffic. It's implemented using fiber channel between switches, it's called a switch fabric. Ultimately, it's transporting SCSI storage commands. So SCSI stands for Small Computer Subsystem Interface, Storage Interface, I think. Goes back a long time ago, and it was a means of sending commands from a storage adapter in a computer to a disk drive. And there's a whole bunch of commands. There's a command set about writing data to disk and making sure that it got written properly, and so on and so on and so on. And so the whole storage command concept of SCSI got borrowed, and because it had already been written and designed, and got dumped on top of an entirely different transport mechanism. So rather than the disk drive being attached directly to the controller, the disk drive is now not really a disk drive anymore. It's a storage array hiding someplace else, and you've got this long piece of complicated string running TCP/IP packets or fiber channel frames from the system that's talking to the storage to the storage itself. So iSCSI uses TCP/IP as the connectivity. The storage elements can be dedicated storage arrays, or indeed there can be any server offering storage at block level, including virtual storage devices. Ideally, within data centers, you'd be using dedicated Ethernet switches, probably using 10 gig or faster network infrastructure, and it's only running data traffic. It's not mixed up with all your other traffic. If you're going to run iSCSI at low bandwidth and mix it up with all your other traffic, you're opening yourself up to a lot of trouble with latency and bandwidth, and it may not perform as well as you like. However, in a small scale environment, it might be just fine for the purposes you're putting it to. It might also be at the higher end, cheaper than doing it with fiber channel, but it probably won't quite get you the same level of performance, particularly from a latency point of view. And latency matters because that's largely the thing that governs your peak I/O rates. Fiber channel, it's using a switch fabric using cut-through switching. So cut-through is different to Ethernet switching. So with a fiber channel switch, you've got dedicated ASICs on board. ASIC is an application-specific integrated circuit. And cut-through switching is where the ASICs have read the header on the frame, and it's already starting to push the frame out of the target port before it's finished reading it in on the coming in port. And that drives the latency down. So usually by using fiber channel, you'll get lower latency than you will using iSCSI. And the host bus adapters are different. So it's not a network interface, it's a fiber channel HBA in the servers. The addressing is different. It uses worldwide IDs, not MAC addresses or IP addresses. You set the switches up using a thing called zoning, because that establishes the connections between the worldwide IDs and within the switches. And the storage is served from dedicated storage arrays. So iSCSI is a lot more general purpose. Fiber channel is rather more specific purpose, but has the possibility to give you better I/O performance. And a lot of the big stuff that I've been working on is fiber channel. Give you a feel for this stuff we've been doing recently. We've managed to drive the write latency down to about 0.15, 0.2 milliseconds, which means we're hitting about 5,000 IOs a second, which is pretty good. Actually, it's very fast. And then storage arrays, the controllers in the storage array connect to the servers through the fiber channel or iSCSI mechanisms. Controllers typically have large mirrored and protected cache in them to hold the data. And the neat thing about that is that once the data is in the cache, the controller can return IO completion status to the operating system back in the server and say, yep, got that data, thank you very much, next. And then in the background, the controller moves the data out of the cache, out to the storage units. Obviously these days with SSDs, that's going a lot faster than it used to. And so cache saturation is much less likely. And the controllers can do funky things like implement RAID across all the available storage elements, making sure that all your data is written to multiple places at the same time. They're operating at block level. There's a thing called provisioning comes into play as to how much storage you can present to the attached servers. There's a fashion for thin provisioning in a lot of cases. So you kind of oversubscribe the storage array on the grounds that you don't use all of the blocks or all of the devices all of the time. But if you ever do, then you need to make sure that you're fully provisioned. And then you present the storage from the storage arrays to the servers using LUNs and UDIDs and all sorts of other clever stuff. There's loads here to go away and read about. And a lot of storage arrays these days will also do built-in encryption and protection of data at rest, things like that. Quite neat. Back in the days of spinning disk before SSD, you would usually do things like RAID 0+1 for best performance rather than RAID 6, because it shows down the bottom here. Then the controllers only had to keep track of where the blocks were. They didn't have to bother about computing parity and all sorts of other stuff. But the neat thing about the array controller is it's a bit like having a RAID controller in a desktop PC. It hides the behavior of the physical storage devices behind that, as I say, disks. And then distributes the IO load across all the multiple storage devices. That way you get more parallelism, underlying principle again, and you get more throughput as a result. So now let's look lastly at some of what's going on with processing. So servers look at storing the data, they process the data, they exchange data with other stuff and users. CPUs do the work, memory holds the instructions and data, storage subsystems out there do the data thing, and data networks let us talk to them. So this is a pretty simplistic diagram kind of showing what happens in conventional server computing. You've got an operating system, you've got a bunch of cores, stuff's running on it. This is a fairly high core count machine. You've got lots of network paths going in and out. They might well be VLAN out to the data networks and LANs out to the users. And you've got lots of storage paths out to the storage arrays over the storage area network, and all the data sets living out there on the storage arrays. In terms of hardware platforms for servers, there are some workloads that just need massive high performance computing machinery. Big high-end multiprocessor systems with very, very, very low latency, very high CPU counts are needed for certain kinds of workloads. Very secure or very mission critical and safety critical environments tend to have very, very, very isolated standalone systems. So running on virtual machines, things like that is too complicated. There's too much to go wrong. You strip complexity away and you're running on dedicated machinery, straight on hardware. There's a current trend for high core count, large memory machines being used as virtualization hosts in the cloud. And that's how we can exploit all this hardware. Virtualization is great for a lot of things because we can make much better use of the available hardware resources. And it gives us a moderate amount of availability improvements as well, because we can spin the virtual machine up on a different host if the host goes pop. Lots of good stuff going on there. It's also worth bearing in mind that one size does not fit all, and that different operating environments, Linux, Windows, VMS, HPUX, all of these different operating systems do different jobs, behave in different ways, and they might do a better job than one of the others, depending on the circumstances. So you can't easily state that all our estate is going to run this or all our estate is going to run something else. You've got to be aware of the nuances and the possibilities. Then we virtualize all the processing. Just talked about that a little bit. Virtual machines, it's just a an application running under the control of a hypervisor. And then within that, you've got the guest OS running inside the virtual machine. It maps onto something that's ultimately scheduled by the hypervisor, and so on and so on and so on. So this is the hall of mirrors effect that's going on. And each virtual machine is a workload. Then you've got containers coming into the scene as well. Containers are kind of lighter weight version of virtualization in a way. But you still have to understand what the interactions are, what's going on when your host hardware runs out of resources or you start moving workloads around. And this is where understanding the behavior of the whole infrastructure gets really important from an availability and performance and security point of view. It's also possible if you pour too many virtual machines or containers into one host to create yourself a host you can never work on because they've all got overlapping operational requirements. So individually, each thing might, only be needed 18 hours a day out of 24, so you've got 6 hours to work on stuff. But if you've got loads of them and they all overlap, you can easily create yourself something that you can't ever work on because it's needed 24/7. So you do have to think about some of this stuff. You also have to think about cloud because you don't really know where your data is. Big thing about cloud is generally it's a bit like home working, we're all terribly dependent on our network connection. If the network connection goes south, sorry, you've just lost your connection to the world. Bandwidth and latency govern the behavior you get, just as much for home working and me doing a talk like this from my office at home as it does in a big data center. Next one's a really important question. Does it matter where all your stuff runs and your data is stored? Well, yes, it does, because you might want to worry about the jurisdictions and your cloud provider's ability to run stuff out of your local jurisdiction from a data protection and a privacy point of view. And what level of resilience do you get? What's going on behind the scenes? There have been a number of fairly high profile outages of some of these things. And so you might want to think about exactly how you handle resilience and availability. Might even want to start thinking about having multiple cloud providers and making sure your data is copied between the two. Then you're running out of different locations, different jurisdictions, all sorts of stuff. So it's not just a case of shoveling stuff off into the cloud. You kind of want to think about what's going on and where it is in order to get the necessary level of availability and performance and data integrity and so on and so on and so on. So to wrap up, as a designer, how can we segment the system to minimize all these interesting little things? And what can we do to protect ourselves? Bearing in mind that if something fails, it's usually the recovery from failure that's got the most impact on the performance behavior. And it's worth considering these two things called RPO and RTO, recovery point objective and recovery time objective, which are around how much loss of service can we tolerate and how much data are we prepared to lose along the way. So banking systems might have a very different answer to, Amazon shopping. Clearly with a bank, you don't want to lose any data because that's bad. Whereas Amazon might tolerate losing a few transactions, but they sure as hell can't tolerate the service being unavailable for a while. So RPO and RTO are concepts worth exploring when it comes to systems and infrastructure. So that pretty much summarizes it. There's this huge pile of underlying layers. I hope I've given a bit of a skate over the surface of all these things that are hiding under there. Terrifying thing is, in most cases, it all just seems to work until, of course, something stops. And that's when it's really helpful to have people around who've got a good idea of where to look and the instrumentation all the way through it in order to give them information in order to know where to start looking for problems. So instrumenting this little lot is absolutely key when it comes around to troubleshooting, especially in the mission critical world where the systems are going to do their best to hang in there because there aren't any single points of failure. So that pretty much wraps the talk up. I'd like to leave you with that thought, which is usually get what you pay for. Choose two, it won't be the third, usually.
Yep.
So here we go.
Thank you very much, Colin. That was great. In fact, if you could, is it easy for you to flip back to that final picture? Only because I really like it. Only because that's just a classic. You've got to love the classics. So firstly, on behalf of the branch, thanks very much for that. This is an area where I don't often venture, but I really should venture a lot more. So I'm a software engineer myself. So I know that, well, you touched on it already, you know, this kind of stuff just works, and I pretty much rely on that. Having said that, you mentioned a load of areas where I've kind of forgotten that I worked. So I worked on jumbo frames quite a lot. I worked on VLANs quite a lot. I worked on a few other things that you mentioned, and I had kind of, no, I hadn't blotted them out of my mind, but I'd worked them and forgotten. So I worked in telecoms and that low-level networking stuff more often than I choose to remember. So,
Yeah.
so thank you very much for that. I've got some questions. We might run out of time. I'm not sure if we get booted at 3:30. I don't think we do, but we might, I guess. So please, audience, please do add any questions if you have. But I'm gonna throw in a few questions to open up, and they might be the only ones. So I've got some comedy questions. The pots and pans things I want to touch on at some point, because I think I know what pots and pans stands for, but I always wanted to know if it was really true. But I won't do that one just yet. So you started out by saying something like it's not engineering. And that really rang true with me, because certainly from a software engineering point of view, we see something that's quite similar in that we are, to some extent, rightly viewed as the poor relation in the engineering community. I noticed at the start that you're a chartered engineer, I'm a chartered engineer, but it's not common, certainly in the software world, to be chartered, to have people doing the stuff that are chartered. And I think there's a great deal of truth in what you say about it not being engineering to the same thing. But so I'll turn this into a question. You also mentioned the word fail-safe, or you said something about failing safe, and that touched me, because the fact that we have fail-safe as a fairly common English word that probably has a root that most people don't really understand as being fail-safe means fail-safe. When it fails, it's still safe. And this is really an engineering word. So the question is going to be, is the fact that we exploit engineering so much in common society, and the fact that what we're talking about here in both software and IT infrastructure is the fact that that's not engineering, does that mean that we've got more work to do? I realise this is a leading question. I'll make no apologies for this being a leading question. Does it mean that we've got more work to do to turn the IT industry into more of an engineering discipline?
Oh, I'm utterly convinced that we have to. Bear in mind, my degree is mechanical engineering. I fell in computing is my second career. I fell into doing computing because of playing around with things like power stations. And, you know, a bug in your code isn't, oh, damn, that's a bug in my code. It's a large lump of metal getting out of control and doing a lot of damage in the physical world. So all of this IT stuff is really about how it interacts with the physical world. And not enough people, I think, are aware of that. Something else that I also think is really important, engineering has got a big thing about documentation, writing things down. And we seem to be heading in a world where less and less of that gets written about how software is written or put together. Something else about engineering is, well, I describe the current state of software writing as being a bit like where engineering was before Whitworth standardized the screw thread. You know, this is still the art and the craft world. It's not yet working with things that are well constructed, well architected, well written. And there have been a number of attempts over the years to try and improve it. For example, one of the things I think is really important is very strongly typed programming languages. Ada would be a really good example of that. Now, Ada is actually very difficult to program in. If you can get your code through the compiler, it's probably gonna work. But there's something very nice about the discipline of that from an engineering point of view, because it forces you to think much more about your code and about the algorithms behind it. It's also worth, actually, there's another diversion. That great book, The Art of Computer Programming, volumes 1, 2, 3, and I think 4 has come out not that long back.
Knuth.
That's the man. Yes, I've met him several times. And it's mostly, it's not about programming, it's about algorithm design. And that's heading in the right sorts of directions as well.
Yeah.
So yeah, as an industry, I think we've got an immense amount of work to do to get it closer to being what I think engineering is.
As an aside, if you ever use the corn shell, I know, so meetings on the Knuth is really quite impressive. If you use the corn shell, I once had dinner with Corn's niece, so it's not quite the same thing, but you know, it's up there somewhere. So thanks for that. I think we can conclude that engineering is good and we should try and do it. As I've been banging that drum for a while now in my own industry, in my own area.
I mean, another example there. I mean, let's say I've been running one of the things that I think is also useful is the talks and lectures approach. So rather than writing mounds of documentation, which, let's face it, is hellish tedious and boring, one of the ideas I've used over the years, you're welcome to steal it, I'll usually bang a bunch of slides together and give a talk a bit like this to the users of the system as a handover. And and the nice thing about doing that, especially if you record it, is, let's say you're dealing with an organization that rotates people in and out of service every few years. That's available to them because that's probably got greater longevity. The system's going to be there for a while. It's got the longevity and they can reuse that every so often for retraining.
Yeah, good. I think we do that. In fact, I think with that kind of handover presentation, I think we've got and my own, or because it's become a lot stronger in that over the past few years. Or at least my visual of it has become a lot stronger. Thanks for that. So just in case we do get booted, oh no, I think the half an hour is gone, so we're not going to get booted, I don't think. But Andy asks, firstly, thanks for an interesting presentation. I'll echo that. Thanks from everyone. So the question is, how common is remote monitoring and control within the UK systems infrastructure? So I'm not quite sure what we mean there. Andy, if you're still there, do feel free to come off mute if you want to. Oh, let me see if I can do this. Yeah, you can now if you would like to pose that question out loud.
Hello, can you hear me?
Yes, you're a bit quiet, but yes.
Now, with the experience we have during the last 12 months of COVID-19 pandemic and the working at home, I'm wondering if this has caused additional preparation and work for the computer systems infrastructure. So
Andy, I'm going to interrupt you there. You're very quiet. I can just about hear you. If I've understood you properly when you're talking there, the question is really in the pandemic. So due to COVID, are we seeing remote monitoring control? And so I guess, Andy, apologies here if I change your question, but I'm not entirely sure what you meant. You're a little bit quiet there. So there's an interesting question there about how much this remote working has impacted this area. So we're all doing different stuff now. We're all working at home. We're all doing a lot more remotely than we were. What's been the impact of COVID and the pandemic in this area, or has there been any?
There's been a big push to remote working. So let me go back to about February of last year, when with a colleague from the Lake District, we were putting some new systems into service that were going to be turned on around September time last year, and in fact were successfully. The date, we only made 1 week's visit to the data centers at the very beginning in February to supervise the physical installation and make sure that all the wiring was correct, the labeling was correct, and that we could gain remote access to the hardware from the Lake District and from me here in Bristol. What we then did, and we had great plans where, you know, I'd be going up to the Lake District, they'd be coming down here, we'd be going to the data centers, et cetera, et cetera, et cetera. All of that got thrown away because of the pandemic. We did everything by me working from here, screen sharing with the guys in the Lake District. We might spend, weeks doing this. I'm not joking. Several hours a day. And we all had VPN access over a dedicated line straight into where we needed to be. And we were able to, because we planned ahead, we were able to build all the servers from cold, installing the operating system from scratch, backing it up, doing everything, setting up the storage arrays from scratch, setting up the data network switches from scratch. Everything we needed to do, we were able to do without having to go to site. The only thing we had to go to site for was when somebody at the data center organization managed to wire something up wrong. And we got very creative. I even managed, this, if you go cycling, there's a fashion these days for wearing little GoPro cameras on your helmet.
Yeah.
So I actually got somebody wearing with a cell phone and earpieces and streaming video off the GoPro on the cycle helmet.
Yeah.
We were remotely directing the guy working in the back of the racks.
Yeah.
So nobody had to go to site at all. We actually managed to invent all sorts of funky and creative ways of doing everything without going there. And everything is remotely monitored and nobody's had to go there. And we've actually changed pretty much everything several times with no physical access to the equipment.
Thanks. I've just realized, in fact, that what Andy may well have meant is once things are all installed, how often is it that we're never going back? And I would guess that the intent is that once you've done this is heavy kit, this is physical stuff. At some point, someone's got to deliver the stuff and put it all together and rack it all up and wire it all up. But once that's happened, once we're done with that, how often are we going back into dark sites and needing to physically go in, and how much of any kind of control and monitoring can we do over ILO and similar things over these remote connections? I think perhaps that was his question.
Pretty much most things can be done remotely. However, in very high availability scenarios, let's say you're doing firmware updates on servers and things like that, my personal preference is to be relatively close in case you need to go there in a hurry. But in the circumstances like the pandemic where you can't do that, then all of these facilities, we designed it deliberately. So we actually put a spare pair of machines in there to act as load hosts. So there's actually a couple of noddy bits of kit that their entire job, there's one in each data center, their entire job in the world is for us to remote connect to. And then we've even got things like USB to serial adapters in those machines. So we can even get to serial ports on the back of machines.
Wow.
If we have to. So we can actually do pretty much damn near everything without needing to go to site. Now that's especially true if you're designing and building stuff around the world. I've done serial port access to the back of servers in Ohio from my office at home in Bristol, because we've designed in enough of those bits to be able to get little out-of-band networks, some kind of remote terminal console access device, things like that. Just think about all of those things and it's all about pre-planning all of that stuff and making sure that it's there. Most of the time it's never going to be needed, but when you need it, you need it.
Yeah, I'm gonna wrap it up after one more question, which is going to be from me, unless anyone steps in, because my own personal interest these days is largely in digital poverty. I was on a digital poverty call today when something a little bit new came up. In that, so digital poverty for the uninitiated is really the lack of ability to engage with the digital world, and that's for data poverty reasons, for a number of reasons. I haven't got the kit, I haven't got the internet, I haven't got the skills, anything in that area. But there are a load of other areas where it can be difficult. I haven't got the money, I haven't got a chair, I haven't got a desk, I'm at home and I'm sharing a connection, I haven't got a device. But one of the areas that is sort of novel is that the UX, the UI, the interfaces that we provide for kind of unskilled users is maybe not good enough. So I think you touched on a couple of things where you've got some really fairly complex, I need to upgrade this thing, I need to make sure I do all this installation stuff. And you talked about having I've got a modem in my house, I've got a router in my house, I've got this bit of kit from Virgin. In fact, I've got a bit of kit from Virgin in the room next door. and it's a modem and it's a router and it's a firewall, it's a thing like that. Is there any extent to which we still need to simplify that kind of home user kit to make life easier for home users? Because my dad's 80, and when he has to reboot the wireless, that's a chore. And now in lockdown, you say you can do all this stuff remotely, and we're in lockdown and none of us can go into my dad's house because he's 80 and we're not allowed to. So there's a lot of phone calls saying, no, click this button. No, don't do that. And how much do we need to do anything, or is there anything we can do to simplify that unskilled user interface?
There's been quite a number of attempts over. This is a completely different territory. I mean,
yeah.
I tripped over something not dissimilar because my mother sadly died. She was one of the early casualties in the pandemic in February last year. She was in a care home in Edinburgh, and trying to talk to her was really difficult. So I'd actually bought some kit for the care home, and it did kind of work, but most of the technology that's available is not that usable by people who aren't familiar with it. I've got a couple of brothers, they're both technophobes. They'll phone me up with questions, and it's largely because this stuff is poorly explained. Doesn't have a great user interface. It's not simple. The trouble is, it's Occam's razor. You can only simplify things to the point where it's as simple as you can make it. If you oversimplify it, it often doesn't work. So there's this horrible paradox of how far can you go with simplification, and what level of knowledge do you need in order for this stuff to become fairly bomb-proof? About the best example of largely bomb-proof kit we've got at the moment is probably cell phones. But even they have now got horrendously complicated, and then you force automatic updates, as Google did earlier this week, and they all stop working for a bit.
Yeah.
And then people don't understand what's gone wrong, and then the other thing that the other trick the computer industry has managed to pull is fooling people into believing it's their fault if something doesn't work, as opposed to the fact that the darn stuff's not very well designed in the first place.
Yeah, I'm with you. I will pose Jen's question rhetorically, if I may, in case, unless you have a simple answer, but it's really an extension of that last question, which is, to what extent is systems infrastructure designed for accessibilities? Now, I imagine what we're talking about, Jen, here is accessibility for people with non-standard needs for accessibility. Well, if you can be brief. Oh no, we've lost Jen, sorry. Oh no, there we are, just moved up to the top somehow.
Yeah, hi, I'm here.
Right. Yeah, sorry. If you can be brief, do ask, because I don't want to keep people around for too much longer than the hour.
No, it was just I did a call last week, and it was a presentation about accessibility and the way that the thinking of designing applications. If you think about designing for accessibility when you're designing the application rather than afterthought, it seems to benefit everybody. So is that sort of systems infrastructure design thinking moving into the systems design world?
Yes, it is, but equally, the systems infrastructure stuff is kind of transparent to the end users. If it's done well, nobody would notice. And the people who are going to be working on it, because of the level of knowledge and understanding that's required, it's still important that you can make it accessible, because you may have people working there who have needs. I mean, for example, I've got a really good friend, Anders, in Stockholm. He's got macular degeneration to the point that he's blind, but he's still one of the world's best operating system designers. And he can still write stuff and find his way around stuff, even though he can't see it. But the infrastructure pieces, you can simplify a lot of things, but really I think the accessibility bit is far more around the kind of discussion we were just having just now, around the end user devices and the intermediate pieces, and maybe the visible pieces that would be within the home infrastructure rather than the kind of stuff you're going to find in the big data centers.
Yeah, I think the key there is maybe that the vast majority of people, even considering only the people who work in our industry, the vast majority of the people who work in our industry don't do that kind of thing. I don't, I never have. So one final thing, James comments that accessibility costs money, and as you mandate it, won't happen. And I think perhaps, James, then if I can cover this one a little bit, is that until we start seeing now that diversity and having a lot more people involved in doing stuff gives good results. Now, maybe what we can do is stress that and say, well, if we have more, if we open up accessibility for all these jobs as well as for users of these services, we'll get more people involved and we'll get better results. You know, you have a diverse set of people working on stuff, and it's better because more viewpoints is better. But Colin, very, very briefly over to you. Apologies. So accessibility costs money. Until it's mandated, it won't happen. So have you got any thoughts on that?
Not particularly. Having things accessible for lots of different people is really important.
Yeah.
But equally, it's a bit like having specialist jobs, like, you know, confined space working or something. There are some kinds of work where there are, going and working in a data center, you've got to be able to get through the airlocks. You've got to be able to get into the back of the racks, things like that. I'm not sure it's possible to do all of the accessibility stuff that you might like to be able to do.
Thanks for that. I think we covered that one. That was really quite well, not very off topic, a little bit off topic. So I know we've gone considerably over, and we are seeing people drop off now because we've gone considerably over our time. But thank you very much, Colin. Thanks very much to the audience. I hope that was useful. I hope that was interesting. I certainly found it so very useful and interesting. So there'll be a recording that I will stop now, and that will appear at some point in the future. I'm not quite sure when. The BCS will do that for us. But that's it. So I will just finish now by saying, Colin, thanks again for that. For the remainder of the audience, final Thursday of the month will be our regular slot for this. Next time we have Pete King from HPE, who's a colleague of mine, in fact, talking about project management. So thanks all for your time.